So here we're going to do a series of 3 videos that show the calculation component strategies for some sulfides. We're going to start out with pyrite. So let's say we have pyrite FeS2, but it's not pure pyrite. Let's say it dissolves a little bit of arsenic into it. And so let's say we have an analysis where we get this. The sulfur content is 53.61 weight percent, and the iron content is 45.72 weight percent. But let's say there's a little bit of arsenic, 0.82 weight percent. So all these values are in weight percent. So what does that mean? Whatever weight units we take, whether it's pounds or kilograms or whatever, let's say we have grams. Well, if we have 100 grams, then 53.61 grams would be sulfur, 45.7 grams would be iron, etc. Now, we want to be able to write the formula, the precise formula for this guy. This is a general formula. It's not going to apply here. A more general formula would be iron, arsenic with 2 sulfur atoms. But we want to be precise. We want to put subscripts where we have Fe sub x and arsenic sub y, and we want to know what those x and y values are for this particular case of this particular pyrite that's been analyzed here. Well, the way to get the molecular or atomic proportions is to divide by the molecular weights. So we'll take these weight percents. Let's just say they're in grams. These are the molecular weights in grams per mole. Sulfur would be divided by 32.065, and iron by 55.845. It's supposed to be a 4 right there, and then arsenic by 74.922. These are all in grams per mole. You can see that the grams will cancel, then we have 1 over moles, and so when we divide these out, then the resulting units will be moles, and we'll get 1.672 for sulfur and 0.8187 or thereabouts for iron, and 0.0109 for arsenic. So that would be in moles. Now we will call these will all sum to 2.5018. We're going to call these the mole proportions. Just abbreviate PROP. They're proportions, not really a mole fraction because they don't sum to 1, but we can turn them into a mole fraction by dividing everything by 2.5018. This is called renormalization. So we'll divide this by 2.5018, and this by the same, and this by the same. And we're running out of room, so we'll erase the chalkboard, and what do we get? So for sulfur, we get 0.668, and then for iron, we get a value of 0.3316. It's a 6 right there, and then for arsenic, we get a value of 0. Oh, that's not correct for iron. Iron should be 0.3272, and then arsenic is 0.043. It's the sum that is 0.3316. Got a little bit ahead of myself there. So this is the mole fraction. So all we've done is taken the mole proportions and divide them by the sum of all the atoms, which is 2.5018, and so we get these 3 values. Altogether, these sum to 1. So if we take the sum of all 3 of those, they sum to 1. This 3316 is just the sum of iron plus arsenic. So why do we care about that? Well, let's take a look at the general formula again. Iron, arsenic, S2. And let's compare it to these mole fractions. How many cations do we have? Well, we have a total of 1 over here. Any combination of iron and arsenic will do. And then we have 2 over here, 2 sulfur atoms. So that is a total of 3 atoms. 2 out of the 3 atoms, 2/3 of the atoms are sulfur, and about 0.668 is what we would expect then. This is a pretty good pyrite analysis because we would expect 2/3 of the atoms to be sulfur, and indeed they are. 667 would be a little bit closer, but we've got rounding errors and probably a little bit of analytical error as well. So if we really do have a pyrite, and would seem to be, since the sulfur is just the right amount, just the right fraction of atoms, then these 2 fellows here should sum to 1. Well, they don't. I gave away the answer earlier. They sum to 0.3316. So what if we take the amount of iron that we get, 0.372, and divide it by 3316. So we're going to renormalize. Do the same thing for arsenic. Arsenic is 0.0043, and we'll divide that also by 0.3316. Then the value we get for iron is 0.9868, and then the value for arsenic is 0.01319. Now I've carried this out to several decimal places. There's probably a lot more precision here than there truly is in the chemical analyses. So we'll just round this off to 0.987 and this to 0.013. So if iron and arsenic sum to 1, they would have these proportions. Let's erase the chalkboard again. So if we wanted to write a precise formula, not the general formula like this, but instead a precise formula, it should be A2 for the particular iron arsenic solid solution that we found, then would be iron with a subscript 0.987, and then arsenic with a subscript of 0.013, and then sulfur 2. Notice that these together sum to 1, as we forced it to do when we did the renormalization. So this is the way we could write the precise formula for the specific case of the pyrite that was analyzed that we showed in the very first frame, where we had a little bit of arsenic solid solution. We checked that sulfur was equal to 2/3 the total number of atoms, which verifies that this is indeed pyrite, and that meant that these fellows must sum to 1, at least if we write it on the basis of 2 sulfur atoms. So we renormalize that total so that they do sum to 1, and that gives us the final precise formula.